Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 37 and the topic of this lecture is subthreshold swing and transconductance. So let's look at the outline of this lecture. We will be looking into what is the meaning of subthreshold swing. Then if you include interface trap charges, how does your subthreshold swing changes, and what methodology do you need to adopt in order to improve subthreshold swing. And then we will also look into the final part, which is transconductance at 1, 2 and 3 region. We will define these regions as we move along. But primarily we will be looking into SS. Whenever we write an SS, we say subthreshold swing and transconductance GM. Initially, at the very first go, let me define each one of them, which I have already told you in our initial classes, but nonetheless, there is no harm in repeating that transconductance is given as change in the drain to source current with respect to gate to source voltage, right. So, typically you give signal on the gate side and you try to extract the current on the drain side. So, this is the drain end which you are getting and this is the gate end at which you are actually inserting the signal, correct. Now, obviously, higher the value of GM, more sensitive the device is to input signal, right, to input signal. Now, the input signal is more sensitive. Why? Because as you start to give, which means that if a GM is large, even a small change in the gate to source voltage will give rise to a large change in the value of IDS. Why is it important? Because when this IDS actually goes to the external circuit and it multiplies with the resistance, the potential drop will be also larger here. So, therefore, what we define as the voltage gain in an analog circuit is given as GM times RD, right. And hence the reason why we need to thoroughly study the transconductance and its effect on circuit analysis. So, that is one thing. Now, let us come to subthreshold slope. Just to give you a brief definition, we will go deep dive into it later on. Subthreshold slope primarily means that, subthreshold swing actually means that how much amount of gate voltage you need to actually insert in order to change the current, right, change the current by 1 decade, right. To change the current by 1 decade, how much amount of change in the gate to source voltage is required. 1 decade means, let us suppose if the current was flowing at 10 to the power minus 3 and you drop it down to 10 to the power minus 4, then the amount of gate voltage which is required to do it is defined as my subthreshold swing. Now, typically we will see later on through formula as well that its value is actually equals to 60 millivolts per decade at 300 Kelvin, but that is at 300 Kelvin. Since we are working with cryogenics, we will see how the voltage changes or how the subthreshold swing changes at a lower and lower temperature. So, with this outline I told you, let us deep dive into subthreshold swing. Now, this, if you look at the first paragraph here, it quantifies how sharply the transistor is switched off by the gate voltage, right, and it is basically the inverse of subthreshold slope, right. And as I discussed with you in the previous slide, it is basically gate to source voltage which is needed to induce a drain current change of 1 order of magnitude. This is how you define your subthreshold swing, right. And subthreshold swing S is basically inverse to the subthreshold slope. So, you try to find out the slope of ID versus VG, 1 over that will give you the subthreshold swing, right. So, let us find out how we can find the value of the subthreshold swing. Now, 1 order change in the current, that is the sort of a benchmark which has been introduced. You must be aware of that when you apply a gate voltage on the metal side of MOSFET, you end up losing at least one flat band voltage before the voltage is visible onto the silicon dioxide interface. This flat band is primarily because of the metal semiconductor contact which is there. There is a flat band voltage difference which happens, and therefore, the effective gate voltage visible to you is basically Vg minus Vfb. So, out of the total gate voltage which is visible to you, this is not an inversions accumulation, it is just a standard way of looking at it. Now, therefore, this is the amount of voltage which you see at the edge. But please keep in mind that there will be also a change which will happen because of the surface potential, and that is what is shown in the right hand side. So, the effective value is psi s, which is surface potential here. This is surface potential, right. VFB is my flat band voltage and Vg is the applied gate voltage. So, when you say applied gate voltage, it is with always with respect to the source which we say. VFB is the flat band voltage which you see, and psi s is the surface potential. This is simple way of saying that charge neutrality and potential is always conserved in a system, right. And this is basically your phi ms which comes into picture, which also depends upon the value of psi s. So, if you look at the right hand side, the variable is basically the psi s, the surface potential. On the left hand side, it is the bias which you give. VFB is again a function of the material which you choose. Gate voltage is the input voltage which is given by the user, and psi s is actually a device level potential which is seen at the interface of silicon dioxide interface, and Na is the acceptor ion concentration. Cox is the oxide capacitance per unit area. Now, therefore, if you do dVg d psi s, which means that you try to differentiate this equation with respect to psi s, I get an expression which is something like this, and which can be therefore written as this, right. If you divide the numerator and denominator by Cox, I will get 1 plus Cd by Cox you will get, and the Cox obviously this will be equals to dVg d psi s, right. Cd is basically the depletion capacitance. Now, I try to explain to you what is depletion capacitance in order to understand what the whole idea is all about. So, if I have this source drain, I have this metal layer, oxide layer here and a metal, and what happens is as you start giving the gate voltage, let us assume that my substrate is grounded, right, it is grounded. Substrate is grounded primarily meaning that you are not giving any potential on the substrate side. When the substrate is grounded and you go on applying the gate voltage, so this is p type, right, and you want to make it n type. This is basically enhancement mode n type transistor which I am talking about. So, if you go on increasing the gate voltage, so this is positive gate voltage which you are applying. So, electrons from the substrate which are minority current carriers will be pulled here, right, and the holes will be pushed backwards, right. So, there will be a sort of a p-n junction which will be formed. So, there will be, let us suppose, an equivalent electron here if I do not apply a bias. This is grounded, this is grounded, and let us assume that there is a bunch of electrons which is coming here. Therefore, there will be a depletion region which is something like this, right. This will be the depletion region. Now, this depletion region's capacitance is referred to as Cd, and this is basically a bias dependent capacitance, because if you change now on the drain side, if you go on adding potential on the drain side, you will be basically reverse biasing this depletion region on the substrate to drain, and therefore, this will actually insert into the inversion region, right. That is what you all are aware of, that the inversion region will actually will go down to a very low value, right. The depletion region will extend more towards the drain side and it will go down to a very low value on the source side, right. Those source is grounded, and since bulk is also grounded, so it is basically the VB0 between the n plus p region on the source side which is responsible for the depletion region. Now, Cd is assumed to be that the depletion capacitance which is there. So, basically if you look carefully, how the gate voltage varies with respect to the surface potential is given by this formula. So, if you actually do d psi dVgs, right, d psi dVgs, then this comes out to be 1 over 1 plus Cd by Cox. That is quite interesting, right, because which means effectively that as the depletion thickness increases or the depletion capacitance increases, there is less sensitivity of surface potential on VGS, right, and that is expected also, because if you go on increasing the depletion thickness, the surface potential will not behave in the same manner, as it will behave less intensely as when the depletion region was not there. Similarly, if you make a C oxide, Cox is again, if you remember from our previous discussion, is basically epsilon ox Tox by A by Tox, right. So, if you make your Tox go higher, this falls down. Well, this falls down means this actually goes down, means this actually goes up, which means this actually goes down, right. Which means that if you make your T oxide go high, d psi s dVg will also go low, and that is expected also, which means that if your oxide thickness increases, you start losing control over the channel, right, and therefore, any change which you bring on the gate side will be reflected less on the silicon dioxide interface, and that's the reason it will have less amount of sensitivity in a sense, right. That is known as basic idea. So, by definition, the swing can now be calculated as natural log 10 dVg d of ln of id. Why? Because id is generally in log scale, and therefore, and natural log 10 because we were saying that we require an order change in the current, and therefore, from there I get final expression as ln of 10 kT by q Cox plus Cd by Cox, right, and that comes out to be 1 plus Cd by Cox. So, even the if you look at limiting to T oxide equals to 0, then my Cox goes to infinitely large value, right, and therefore, the overall S value which comes out will be ln of 10 just kT by q. kT by q is 25 millivolts if you remember at 300 Kelvin, right. So, and this is actually the PN junction diffusion current which will come into picture, which means that when oxide thickness tends to go to 0, which means that there is no oxide available, it is just the metal and the interface. So, the IV characteristics then becomes almost like a exponentially PN junction diode characteristics, and that is true also. If you remove the oxide thickness, it is just nothing but P plus. So, if you remove the oxide thickness, it is nothing but P plus N P plus, right. These three terms come into picture. So, there are two back to back connected diodes, and therefore, the behavior will be almost like a characteristics of a exponentially rising function of a PN junction diode. Keep in mind here, because this is more of a cryogenics course, keep in mind that the S value, the subthreshold swing value, depends on the temperature as well. It is, and you can show its kT by q term here, and at T equals to 300 Kelvin, this value comes out to be approximately 25 millivolts, right. And as you lower the temperature, this will go on reducing drastically lower and lower. So, typically we are assuming that the subthreshold swing value which we are going to extract will have a sort of a dependency on the oxide thickness, will have a dependency on the depletion thickness, and so on and so forth. Please also keep in mind that when you have the full inversion layer being formed, there will be a screening effect which will happen, and therefore, post that Cd will not change drastically to a smaller value, right. So, till a time Cd is a function of the bias, this formula holds good for a subthreshold swing calculation. Now, so let's look one more thing. So, if I divide this, I will get, as I talk to you, my final value of S will be ln of 10 kT by q, right, and if you divide by C oxide, I told you this will be Cd by Cox. So, as I told you, if Tox equals to 0, then epsilon ox goes to infinitely large value, and so epsilon oxide layer thickness into area by Tox, right. So, if this goes to 0, right, this becomes very large, capacitance suddenly increases. As the capacitance value suddenly increases, this quantity goes down, and therefore, this whole quantity on the parenthesis goes to a 1 value, because this goes to a 0 value, this goes to 1 value, which means that S equals to kT by q ln of 10, almost like a diffusion current which we have seen. So, the end point of this is that when the oxide thickness is non-zero, the subthreshold swing degrades, right. It is 1 plus Cox by Cin will degrade, right, and therefore, that is the problem. So, lower the value, better it is. Please understand this point also, that low, because then the swing will be faster, right. If S is smaller, obviously you will get a much faster swing as such available to us, and that is the reason I say that S will be ln of 10 kT by q Cox plus Cd. Now, so you see, if you break it down into basic equivalent circuit, then there is one Cox here and there is a depletion here. So, this is Cd and Cox, this is VGS, and this is, let us say, bulk, which is, let us say, grounded. So, I have such type of network available here, and this is where your surface potential applies. So, surface potential is basically sort of a voltage divider between Cox and CDS, right. So, there are two capacitors in series, one is Cox, another is the depletion layer capacitance, and the potential at the center of the two is basically governed by the voltage divider network of these two capacitances. The degradation factor is given as Cox plus Cd by Cox, right. So, higher the value of Cd by Cox, more will be the value of subthreshold swing in a sense, and worse will the device performance be. And therefore, if you want the swing to be as low as possible, try to make your CD or Cox. So, make your CD as high as possible and Cox to be as low as possible. That will ensure that your subthreshold swings are larger. Now, as I discussed with you, therefore, this factor appears directly while illustrating the voltage division across the oxide in the depletion layer. So, typically this gives me sort of a mechanism by which it tells me that this much amount of charge will be there in the oxide layer, this much amount of charge will be there in the depletion layer. Further, since the depletion width also varies with the gate voltage, the subthreshold swing is not perfectly constant, but has a weak dependency on the value of the gate to source voltage. This we just not discussed, that if you change your gate to source voltage, my CD will go on changing, the depletion capacitance will go on changing, because it is a function of the inversion layer capacitance and other things, and therefore, it is a weak function of the gate to source voltage. Now, let us not because it is important when you do cryogenics, let us now to try to bring in the interface trap charges. Now, when you have a significantly large amount of interface traps density for whatever reasons, be it fabricated when you properly non-annealing, or there is some problem in terms of temperature fluctuations, or the type of distilled water used is not very good quality, there will be an associated capacitances which is because of the interface trap charges, right. So, initially you had a depletion capacitance, now there will be also an interface trapped based capacitances which will basically be in parallel to the depletion layer capacitance. So, what happens is the total depletion capacitance becomes CD plus CIT, right. CD is plus CIT, CD is the depletion layer capacitance and CIT is basically the interface trapped capacitances. And higher, obviously higher the value of the interface trap density, more will be the value of CIT, and therefore, more will be the effective value of your CD. So, if I write down CD sort of effective value, it comes out to be equals to CD, which is post without any interface trap charges, and CIT. Moreover, at this stage we will not go into details of that, but just to keep in your mind, CIT, the interface trap density, is also a function of like where you place the interface trap charges. If it is very close to the oxide layer, if it is very far away from the oxide layer interface, its effective value also changes. Keeping that apart, we just look into the value of the DIT, from there we find the value of CIT, which is the interface trap charge density. So, if you substitute this value into our new S with DIT, I get this, right, and therefore, I can write down S with DIT to be equals to S without DIT multiplied by this quantity, right. Now, you can find out yourself and get the value. So, this is S with DIT, the first term here is S with DIT, and this is S without DIT, which you found out, and this. So, this is a conventional DIT which I found out, and this is your sort of a correction factor which comes into picture, which is Cox plus CD. Now, if you see here carefully, the subthreshold swing actually degrades with CIT, and it is expected also. That let us look at physically also. If you have interface traps being generated, then you require a larger gate voltage in order to remove the charges from the interface trap charges to make it inverted, right. And that is the reason there is a degradation of the S with DIT. S means subthreshold swing with interface trap charges, it shows a swing. Now, let us look at the method to improve the subthreshold swing, right. So, my whole aim is to reduce the subthreshold swing. One good way and very pertinent to the topic which we are doing is just simply go to low temperature. When you go to low temperature, obviously KT by Q term goes down and your S value goes down, right. You can also increase the value of Na and thereby lowering your CD value, right. Similarly, you can raise the value of C oxide by thinning your oxide thickness. And if you consider the interface trap charge density, a low interface trap charge density will ensure to you that your DIT is small, and therefore, subthreshold swing with DIT appears to be relatively weak. Now, there is another way of doing it, which is if you apply a substrate bias, right, VBS. Now, if you apply a substrate bias, that increases the surface potential, right. Why? Because let us suppose you apply a positive gate bias and you apply a positive substrate bias. So, positive substrate bias will do what? Is it will try to pull the electron, right, towards itself. So, you require to give a much more larger gate voltage in order to invert the channel, and that is the reason surface potential also increases. Now, when you apply a substrate bias which is, let us say, positive in nature, you basically forward bias the depletion layer or the p-n junction in the depletion layer, and therefore, that goes to that there is a reduction in the value of CD. The depletion layer capacitance actually falls down. Why? Because your VBS, which is bulk to substrate bias, tends to forward bias the depletion region. As you therefore lower the CD value, just put it into the formula, subthreshold swing reduces. So even after you have fabricated the device, and if you want to change your subthreshold swing, the various knobs available to you to do that is, one of the knob is basically your VBS. Prefabrication, TOX is one of them, and doping concentration is another of them. Ambient, low temperature ambient will reduce your subthreshold swing. So these are the few takeaway methods to improve the subthreshold swing, but please keep in mind that these are only to improve the subthreshold swing. So for example, if you have substrate doping concentration I increase, it might affect the threshold voltage of the device, right, adversely or in favor. We will not go into details of that at this stage, you possibly might know, but it might change. So these methods are not only change the subthreshold swing, but may even change the other parameters. So be careful while choosing these parameters and applying some potential to it or some expression to it. So let us look at the low temperature effect in the subthreshold swing in an n-channel MOSFET. On the left hand side figure which you see, it's basically drain current in log scale versus gate voltage, right from 10 Kelvin to 300 Kelvin. This is 10 Kelvin and this is 300 Kelvin. This is for bulk N MOSFET, and these are all experimental data which has been taken from the paper here. And this is on the right hand side is basically the subthreshold swing versus drain current, right. And interestingly, at very low drain currents, the subthreshold swings are almost constant independent of the current, right, be it low temperature or high temperature. Effectively, two things you should be very careful about. One is that at low temperature the subthreshold swings are much lower. You see, if you look at here particular point, the subthreshold swings are much lower, around 20-25, right. Go to 300 Kelvin, it is about 80, right, and this is typically 0.5 micron device, not a very short channel device. However, as you make your current, drain to source current, go higher and higher, you see your subthreshold swing shoots up suddenly to a very large value. For the discussion for this case is that as the temperature decreases from 300 Kelvin to 10 Kelvin, the subthreshold swing drastically improves as you go down, right, and because it is directly proportional to temperature, lower the value of T, lower will be the value of KT by Q, lower is the value of SS, right. We have already discussed this, I will again point it out to you, might have missed it, that if you look at the left hand side and you see IDS versus VGS formula, there is a small crossover happening somewhere here around 1.2 to 1.3 volts. Think about it, why? We have already discussed this point in our earlier discussion, but nonetheless you should know, you should be able to extract the value here. Okay. So with this we will do the low temperature doping of P MOSFET in our next lecture. So in this lecture what we studied, we ended up having at the subthreshold swing in a detailed manner. On what factors does the subthreshold swing depends. Especially to cryogenics, we found out one important point, that the subthreshold swing reduces with temperature and therefore it makes it a better component in as far as subthreshold swing is concerned. It is much better at lower temperature. However, there are certain knobs by which I can improve the subthreshold swing to a lower value, and that is primarily low temperature, low NA by giving a back body bias of VBS and so on and so forth. Lastly, we saw that for load currents, the subthreshold swing is almost constant, a low value, but suddenly it increases as the current sweeps to a larger value, drain to source current. So which means that post inversion, when you go to the saturation region, the current shoots up drastically to a higher value. So with this, I think I will stop here today, and when we take the next class, we will take up PMOS and then the transconductance. Thank you very much.